Welcome to today's lecture on ratio and proportion. I'm Drew Collip. This lecture will focus on ratios, the next lecture on proportions. Prior to this, we were reviewing the fundamentals of fractions. Now we're going to take what we learned and try and apply it to something new, in this case, ratios. What have we learned about a fraction? Well, we have a fraction right here, and we know the denominator. This is the total amount. How many parts make up a whole? And the numerator, that's how many parts you have. So we can express the fraction as 2 over 3, and we know what that actually means. It's 2 divided by 3. So you can see the notation here. We have 2 divided by 3. But it can also represent a ratio. A ratio of 2 compared to 3. This is our ratio symbol here, meaning 2 compared to 3. So that's what we're going to be talking about today, is ratios. So what is a ratio? A ratio is a comparison of two quantities. And just like a fraction, it's always written in simplest form. So simplify it down. The units should be the same. They cancel out, and then the ratio becomes dimensionless. If the units are different, change one so you can compare the two values. Lastly, make sure you correctly present the quantities in question. For instance, written as such, the 2 over the 3, we know the 2 is the numerator and the 3 is the denominator. 2 is the parts and 3 is the whole. When you're dealing with a ratio, however, you cannot assume that. You have to define which each of those values are. So as an example, here is that fraction we had, 2 over 3. We can represent it as a ratio of 2 compared to 3 or 3 compared to 2. Are we talking about 2 parts compared to 3 total or 3 total compared to 2 parts? So when you have something written down as a ratio, make sure you define what each of those numbers represents. It's not necessary with a fraction because we know the definitions there. The top number is the part, the bottom number is the whole. With a ratio, the numbers can mean anything. Let's look at example 1. Here's a window. It's 12 centimeters wide and 18 centimeters long. AS, write the ratio of width to length in its simplest form. So we're defining width compared to length. So we're dealing with width compared to length. What's the width? The width is 12 centimeters. What's the height? 18 centimeters. What you can see here, we have the same units on both sides, so they can cancel out. And then we can simplify that. If that was a fraction, 12 over 18, how could you simplify it? You could take out a common factor of 6. We'll do the same thing here. This is 2 compared to 3. This is the ratio of the width of the window compared to the length of the window. Now let's write the ratio of length to width. In this case here, our length 18 centimeters, our width was 12 centimeters. Again, the same units, they cancel out. We simplify down the same way. We have 3 compared to 2. Notice those numbers on A and B, they've swapped positions. And that is totally acceptable because unlike fractions, we have to define which value is in which place. Lastly, write the ratio of the width to the perimeter in simplest form. And if you don't remember the equation for perimeter, perimeter is 2 lengths plus 2 width. Perimeter is all the way around there. So now we're dealing with the width to the perimeter. Width compared to perimeter. So what is our width? Our width is 12 centimeters. And what's our perimeter? It's going to be 12 centimeters plus 12 centimeters plus 18 centimeters plus 18 centimeters. We add that all up now, 12 centimeters compared to 60 centimeters. Again, we have the same units. They can cancel out. We can now simplify that. How many times does 12 go into 60? It goes in 5 times equally. So now we have a ratio 1 to 5. So the ratio of the width of the window to the perimeter of the window is 1 to 5. Again, we have to define which each of those numbers are. If we don't, there can be a lot of confusion. Let's try a few more examples here. Write the ratio of 25 centimeters to 1.5 meters in simplest terms. So we're going to write the ratio of 25 centimeters to 1.5 meters. Do you see a problem here? One is in centimeters and one is in meters. We must convert them both to centimeters or convert them both to meters. Let's convert them both to centimeters. This is already as centimeters. This one here, 1.5 meters. 1.5 meters. How many centimeters are in a meter? There's 100. So we have to multiply by 100 to get there. But why does that work? Well, 100 centimeters is equal to 1 meter, right? Here, these two things can be used in a fraction. 1 meter on the bottom, 100 centimeters on the top. We have meters on the bottom. They cancel out. We're left with centimeters. This gives us 150 centimeters. At this point in time, I haven't taught you this. This is conversion factor method. This is going to be a key concept for you to take from this course. For now, I will be satisfied if you can just multiply by 100. So we get 150 centimeters. Now that they are the same units, now we can compare them. Those cancel out, simplify. We can take out a common factor of 25, 1 compared to 6. There is your ratio of 25 centimeters to 1.5 meters. The units have to be the same. Remember that. Let's try this one now. Simplify the ratio of one length of 2 3/4 meters to another length of 6 3/8 meters. Let's write that down to begin with. We have the same unit, so we don't have to convert. 2 3/4 meters compared to 6 3/8 of a meter. This is a challenge, but let's use what we've learned earlier and figure this one out. 2 3/4 meters, what if we just stuck a line in between there? We get a division, 6 3/8 meters. Let's work that out. We're working this out now. What do we get? We get converting this to an improper fraction, as we've done in a previous lecture. Two times 4 is 8, plus 3 is 11. 6 times 8 is 48, plus 3 is 51. Now, we flip and we multiply. And remember, we flip the meters as well. It goes down to the bottom. When we do that, you can see we have meters on the top, because that would be a fraction as such, and we have meters on the bottom. That's why they cancel out. Can we simplify this down? We sure can. Take 1 4 out of there, take 2 4s out of there, giving me 22 over 51. No more units. The units canceled out. Then I can write this back as a ratio, 22 compared to 51. So we can switch from the ratio format into a division format, and when we get our fraction, we can put it back as a ratio. Very simple way to try and simplify two mixed numbers that are being compared. Let's try example 4. Mach is a number related to the velocity of a moving object. Mach 1 indicates it's traveling at the speed of sound. The speed of sound is 340.2 meters per second. Oftentimes, Mach is used in relation to jets. There was a jet called the Concorde, and it could travel faster than the speed of sound. You could travel across the Atlantic Ocean from Europe to North America in a very short period of time. It was specifically designed to break the sound barrier. It's a little known fact that the reason why it never took off here in North America was it was in direct competition with a lot of the American companies. They made it against aviation regulation that passenger jets could travel in the airspace faster than the speed of sound. They couldn't travel faster than Mach 1. That's one of the reasons why the company couldn't get a foothold here in North America. Eventually, there was a very bad plane crash and the company went out of business. Just trying to make this more interesting. So what we're asking for is find the Mach speed of a jet traveling at 275 meters per second. So that's less than Mach 1. And I'm asking you to convert your ratio to a decimal value. Let's compare the speed of the jet compared to the speed of Mach 1. Let's do something similar to what we did in the last one, where I divided it. In this case, we're going to write it as such. 275 meters per second divided by 340.2 meters per second. Once again, you can see units same on the top and the bottom, they cancel each other out. Now we have to get this down as a decimal value. What we're going to do, we're going to multiply the top and bottom by 10 to get rid of any of those decimals, that decimal on the bottom. One easy trick, you multiply by 10 if there's one decimal, and all of a sudden the decimals are all gone. We can simplify down. I can see I can divide the top and the bottom by 2. When I do that, I get 1375 over 1701. That's as far as I can take it in this case. But I could write it as a ratio, 1375 compared to 1701. But that's not what the question asked for. It asked you to make it as a decimal value. What we can do is we can just type that value in our calculator and hit equals. We get 0.8083483, and it continues on. What that represents is that decimal over a value of 1. So I could express this, let's say, to 3 significant digits. We'll talk more about significant digits in the near future, compared to 1. I can compare the speed of the jet to the standard unit of Mach 1. You can see this is traveling a little bit less than Mach 1. The take-home message here is units have to be the same, they cancel out, and we can use some of those techniques we learned earlier with fractions to solve some of these problems. Let's try and make it a bit more relevant. The fundamental laws of chemistry state that elements of pure compounds combine in definite proportions by mass. This is something from chemistry. Pure compounds combine in definite proportions by mass. We're talking about water and hydrogen peroxide. If you had them both on your table at one time in a glass, if you just looked at them, you wouldn't be able to tell the difference. Pure water has a different chemistry to it compared to hydrogen peroxide. Pure water is H2O, hydrogen peroxide is H2O2. If we look at these, there's only 2 elements in there. There's hydrogen and there's oxygen. So if we compare the amount of hydrogen to oxygen in water, we get it's a 2-to-1 ratio of hydrogen atoms to oxygen atoms. If I compare the atoms of hydrogen to oxygen for hydrogen peroxide, it's 2-to-2, which simplifies down to a 1-to-1 ratio. So you can see if I look at the ratios of the atoms of hydrogen and oxygen in these 2 molecules, they're very different. This applies to other chemicals as well. We have CO and CO2. CO is carbon monoxide, CO2 is carbon dioxide. This has a ratio of 1-to-1 carbon to oxygen. This has a ratio of 1-to-2 carbon to oxygen. Carbon monoxide is a poison. That's why you probably have a carbon monoxide detector in your house. If the combustion in your furnace is off, it'll maybe create too much carbon monoxide, in which case your house will fill up with carbon monoxide. As a gas, it's odorless, it's clear, you can't tell it's there. Interesting fact, Weird Al Yankovic's parents died of carbon monoxide poisoning in their home while they slept. CO2, this is not such a great thing to have in your body. That's why you exhale it. Same atoms, different proportions, a different ratio of one atom to another, very different chemistry. Here we have N2O and NO2. We're comparing nitrogen compared to oxygen. This is a 2-to-1 ratio. This is a 1-to-2 ratio. N2O, nitrous oxide. It's an anesthetic. This is maybe what they give you at the dentist to try and calm you down a bit, sometimes known as laughing gas. NO2, this is a pollutant. Not good. So by changing the ratio of atoms, we can change the properties completely of those molecules. Very important concept for chemistry. Let's try and apply ratios to more chemistry. A chemical solution is being made up of 50 grams of NaCl mixed with 100 grams of water. Determine the ratios. So here we want to determine the mass of sodium chloride to the mass of water. So I want NaCl compared to H2O. What do we get here now? We get 50 grams sodium chloride compared to 100 grams of our water. Remember, the units are the same. They cancel out. We simplify down. This gives us a 1-to-2 ratio. So in this particular solution, it's a 1-to-2 ratio of sodium chloride to water by mass. But I could ask you for the mass of water compared to the mass of sodium chloride. In which case, hopefully you can see, this is just going to be 2-to-1. We just flip those around. We could also ask for the mass of NaCl compared to the total mass of the solution. So this is NaCl compared to your total mass. And what do we get here now? NaCl is 50 grams. The total mass, well, we have 50 grams of NaCl plus 100 grams of water gives me 150 grams. Again, same units, they cancel out. And here we get 1 to 3 ratio. We're not done yet. Let's take the total mass of the solution compared to the mass of NaCl. So total mass compared to NaCl. What do we get? It's just the opposite. We get 3 to 1. What about the total mass of the solution compared to the mass of water? So here we get total mass compared to the water. And here we get 150 grams total mass, and the mass of water was 100 grams. Again, grams cancel out, and I get a 3 to 2 ratio on that. Lastly here, mass of water compared to the total mass of solution. So here we get H2O compared to total mass, and that's equal to 2 compared to 3. The purpose of this, hopefully you were bored with this, but you can see where I'm going with this. All these different ratios here, 1 to 2, 2 to 1, 1 to 3, 3 to 1, 3 to 2, 2 to 3. Those are all different numbers. It all is in reference to a single solution right here. So the purpose of this part of the lesson was to try and emphasize when you're writing a ratio, you can't assume that the second number is the whole and the first number is the part. You must define which is which. Don't forget that. Let's try some practice problems now. I would like you to try these on your own. Make sure you have the right value on the right side of the ratio and make sure you simplify it down. Also remember, units should cancel out where possible. So we have 1, 2, 3, 4, 5, 6. So pause your video, see if you can convert these into ratios. Let's take them up. Ratio of 16 compared to 24. 16 to 24. Common factor in both of them is going to be 4. So I can take a 4 out of the 16, it gives me 4. Take a 4 out of the 24, gives me 6. You can see here, this is not in simplest form yet. I can now take out a 2. This gives me 2 compared to 3. So just like when simplifying fractions, it doesn't have to be all done in one step. We can continue on and take values out. What about the ratio of 2 compared to 25? Can I simplify that down? I cannot. Therefore, that is the final answer. In a candy bag, you find out of 62 candies, there are 16 red, 20 blue, 18 green, 8 yellow. What is the ratio of red candies to total number? The purpose of this question was to try and show you there's a lot of information in this question, and most of it you don't need. Part of your skill set in math and science is going to be looking at information and pulling out the relevant information and forgetting about the other stuff. We want to have the ratio of red candy compared to total candy. Red candy was 16, total candy 62. We're not done yet. We have to simplify down. I can take a 2 out of the top and bottom, 81 compared to 31, and we are done. So the ratio of red candies to total candies in the bag is 8 to 31. Notice I had to define the ratio of red candies to total candies is 8 to 31. I could have said the ratio of total candies to red candies is 31 to 8. Both those statements are true, but the ratios are different. Again, make sure you define which is which. In a school election, 4,000 yes votes, 3,500 no votes were cast. Write the ratio of yes to no votes. 4,000 compared to 3,500. One thing we can do real quick is we can cancel off some of these zeros here. We have 40 compared to 35. I can take a 5 out of both of them. 8 compared to 7. So the ratio of yes to no votes was 8 to 7. Next question. Worker A can unlock 10 cell phones per hour. Worker B can unlock 9 cell phones per hour. Express the ratio of the number of cell phones worker A can fix compared to B. So that's important. We're saying A compared to B versus B compared to A. versus A compared to total or B compared to total. Again, you have to define which is which. So here I have 10 phones per hour compared to 9 phones per hour. Notice the units are the same. Phones per hour cancels out phones per hour. I'm left with 10 compared to 9. I cannot simplify anymore. Therefore, that is the final answer. The number of phones worker A can unlock versus the number of phones worker B can unlock. Why would you want to know this? Well, let's say worker A unlocked 1,000 cell phones. Then how many cell phones did worker B unlock? Well, you can quickly use the ratio and determine it would be 900. Number 5, write the following ratios in simplest form. The ratio of 4 nickels to 5 dimes. I wrote this for a reason. This is pretty simple. This is 4 compared to 5. But I could also ask you, write the ratio of the value of 4 nickels compared to 5 dimes. So if I asked you for the value, we could write a different ratio using the same data. 4 nickels, a nickel is worth 5 cents, and a dime is 10 cents. For those of you who are not familiar with those terms, perhaps outside North America, you have different terms to represent these coins. If I have 4 nickels, that's 20 cents, compared to 5 dimes, which is 50 cents. Again, we have the same units. It's both in terms of money. We got rid of our units. Now we multiply both sides by 100 to get rid of the decimals. We can then cancel out 10 here and here, and we have a ratio of 2 compared to 5. So here, again, very simple thing, 4 nickels compared to 5 dimes. How do you want that represented? In the number of coins? Or as the value? Have to define these things. Next up, ratio of 30 feet to 70 feet. 30 feet compared to 70 feet. Again, units are the same. They cancel out. We have a 0 on both sides. We can cancel that out. That gives me 3 compared to 7. Now, that's in terms of feet. If I ask you in terms of centimeters, you can convert those over to centimeters. But there's no need. You'll get exactly the same ratio of 3 compared to 7. Again, another great way ratios can be used. Here's a question here for the pharmacists in the course. I know maybe some of you are coming from a pharmacy background, so I tried to add a question in for you. The price of an antibiotic in one store is $13.75, although the same antibiotic is $7.50. Write the ratio of the prices as whole numbers. So we don't want decimals in there. So let's write down $13.75 compared to $7.50. These cancel out. We then multiply both sides by 100 to get rid of the decimals. We can divide the top and the bottom by 25. I know that. Let's do that now. Divide by 25, divide by 25. And here I get 55 compared to 30. I can simplify that more. Divide both sides by 5. And here I get 11 compared to 6. Quite a bit of difference when you turn it over to the ratio. So once again, with ratios, you should have the same units. If they're not, convert them so they have the same units. The units should cancel out, and then you must simplify down, just like you did with fractions. There's a bit of work you can do. If you haven't done it yet, I'd like you to pause the video after I explain this and do this yourself. I'd like you to measure some parts of your body in centimeters, please. The best way to do that is get a string, measure it out on your body, and then measure that length of string. So I want you to measure, first of all, your arm span. That is from fingertip to fingertip, all the way across. So that is your arm span. I'd then like you to measure your height. This is from top of your head to your feet. I'd like you to measure your navel height. Your navel is another term for your belly button. I want your belly button to the ground. I then want you to measure your forearm. This is your hand to your elbow. So that's this part right here. I then want you to measure your forearm and your hand. So that is your elbow to your fingertips. So make those measurements here. Write them all down in centimeters. I now want you to create some ratios with these numbers. I want you to write your arm span compared to your height. I then want you to compare your height to your navel height. I then want you to compare your forearm plus your hand to just your forearm. I then want you to do some math on that. Convert them into a fraction, then into a decimal. So let's look at an example here. Let's say we measured your height and we got 187 centimeters. We compare that to your navel height, which was measured at 115 centimeters. Let's convert that into a fraction. 187 centimeters divided by 115 centimeters. Notice what we have here? Same units in the top and the bottom, they cancel each other out. We then write it down as such. This is in simplest terms. I cannot simplify that anymore. I could convert it to a mixed number, but what I want you to do here is I want you to divide it. I want you in your calculator type 187 divided by 115. And here I get number 1.62608669. What this would be, this is your whole number, and this would be, I can turn that into a fraction by placing it over a 1. So this would be a ratio of 1.626 if we just take it to 3 decimal places compared to 1. I'd like you to do this calculation for all 3 of these for your heights and see what you get. What you should have got something close to 1 to 1. In this case here, you should have got something close to 1.6 compared to 1. And here you should have got the same thing, 1.6 compared to 1. Interesting fact. Next time someone asks you how tall you are, put your arms out and say, I'm this tall. Now notice, there's a common number here. 1.6, 1.6. This is a special number. Let's talk about it. So far when you've been doing math, you've probably just been adding, subtracting, multiplying, dividing, and solving equations. There's much more to math than just that. There's some very interesting theories about math and some very interesting patterns that exist. Let's examine one of those. This is the Fibonacci sequence. What you can see is the sum of the 2 previous numbers is the next number. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 5, 13. So on and so forth. That is how the Fibonacci sequence comes about. Just like this. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. 21 plus 34 is 55. 34 plus 55, 89. 55 plus 89, 144. And we can keep going. Why did I do all that? I just have that written above here. I wanted to show you something. Let's take the ratio of 2 numbers together. The ratio of these 2 numbers. 3 compared to 2. We'll take the ratio of these numbers. 5 compared to 3. Ratio of these numbers. 8 compared to 5. 13 compared to 8. Keep going. The next one we would compare the 21 compared to the 13. And then we would compare 34 compared to 21. We compare 55 to 34, so on and so forth. What I want you to do now is I want you to take your calculator. I want you to divide those. Put a little line in there, turn the ratio into a division sign. And I want you to write down the decimal. Do that now. 3 divided by 2, 1.5. 5 divided by 3, 1.666 repeating. 1.6 with a line over top. That's how we signify repeating. We put a line above it. 1.6, 1.625, 1.61538, 1.61904, 1.617. Do you see something here? The number's changing, but it's not changing much. If we keep going, we're eventually going to get a ratio that approaches a special number. Let's talk about that number. Now, I'm sure you're well aware of the value of pi. Pi is an irrational number, 3.141592, so on and so forth. And that goes off to infinity as far as we know. Mathematicians have not been able to find a repeating sequence in there. That's very important. You can actually look up pi to 1,000,000 decimal places if you like. There's the website for it. There is another value that exists, another constant like that. It's called phi, sometimes known as the golden ratio. Here's that value here. Just like pi, it continues on as an irrational number. If we kept getting bigger and bigger in terms of our comparisons between two numbers, we would eventually get closer and closer to this number here. This is sometimes known as the golden ratio. Now, if you go back and look at the data you had earlier, you should have seen that your height and your arms were about the same ratio. What you should have also seen is that your belly button to the floor and your head to the floor was a certain ratio, 1.618, give or take, depending on how you measured it, and not everyone is perfectly proportioned. Also, your forearm to your forearm and hand, you should have got something similar to 1.61. It goes much further than just your height to your navel and your forearm to your forearm and hand. Much of your body plan can be measured, oftentimes abides by the golden ratio. More than that, you can see we have the area here of this spiral here, Fibonacci sequence, the ratio. So this area here is 1.16 if this area here is 1. And we can continue to get bigger and bigger and bigger. So you can see if this is 1, then this length, A plus B, is 1.6. There's more to it than even that. Again, we're looking at the ratio of 1.6 compared to 1. If we look at DNA, the major and minor groove of DNA has a ratio of 1.6 compared to 1. If we look at the spirals in plants, in shells, in seeds, in flowers, it's a ratio of 1.6 to 1. Again, the spirals here showing you that Fibonacci sequence. It's crazier than that even. Spiral galaxies are the same. Hurricanes are the same. Even our own CN Tower here in Toronto is designed with a ratio of 1 to 1.6. There's something special about that ratio. That's why it's called the golden ratio. Much of nature has used this value to pattern it. I will post a link to a video in the notes. You can check that out. It's referring to seed patterns and how this pattern here is the most efficient pattern for seed distribution. But it gets even crazier than that. You may wonder why in photography, oftentimes the individual is not in the center of the photo when they're doing ads, because humans tend to appreciate the golden ratio. What about symbols? Twitter, diameter of 1.6 to 1. National Geographic, Chevron, Pepsi Cola, 1 to 1.6, Toyota. And again, all these different patterns here. Your ear, architecture, there are many different things that involve the golden ratio. So these are just some of the amazing things that we can get into when you really start to explore math just for the sake of math. You start seeing patterns and you can start developing some interesting theories. That's all for today. If you haven't measured yourself, give it a try. See what your proportions are like. Until next time.